start recording. Today is 2/5/15. We're going over the comp, stoic, and percent comp FIP. That's terrible handwriting. Oh well. That's the best you're going to get on such a morning. Okay. So in that first one we're asked what's the mass in grams of 3.75 moles of magnesium hydroxide. So first, obviously, you have to know what the formula for magnesium hydroxide is. So it's obviously ionic, because it's just the names of two ions. Well, we have Mg2 plus, we have OH1 minus, which gives us MgOH 2 times. Okay? So from there you can figure out the molar mass. We know we're going to set this up just like any other stoichiometry problem, starting with the given in that first box. And we know that we'll have 1 mole of MgOH 2 times. And we figured out the molar mass here. So we've got Mg at 24.31, oxygen at 16, and we have 2 of them. Hydrogen 1.01, we have 2 of them. So our mass is 58.33 grams per mole. So that's the number that we're going to put up here, 58.33 grams in 1 mole. So we get a raw answer of 218.737, etc. And we only have 3 sig figs to work with. So because we have 3 sig figs, our final answer is going to be 219 grams. 219 grams of magnesium hydroxide. Okay? Questions, comments, concerns? If you had a problem there, do you see where it was? Okay. For many of you, many of you, it was the formula. And if you don't do the formula right, nothing that follows is correct. So, and like I said, you must, and I promise that if you stick with it, you will become so fluent that somebody will say magnesium hydroxide and you will see the formula in your head. You'll think in chemical formulas. So that's the point you will get to, I promise. No matter how much you feel like that's not true. Stick with it, and it will be. And it'll have to be if you're taking college chemistry, because they don't pussyfoot around. They don't write formulas for you. They just say blah, 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 blah. Okay, number 2, how many moles are represented by 565.0 grams of iron 2 oxide? How many moles? Okay, so again, just like any of these, you have to write the formula first. So iron 2, Fe2 plus, with an O2 minus gives you FeO. And people did pretty well on this one, whether it was luck or skill. People did better on this one, and it's not mine to judge. So the first thing we're going to write, of course, is our 565.0 grams of FeO. And we need to find out how many grams of FeO are in 1 mole of FeO. So iron is 55.85, oxygen is 16. There's only 1 of each. Oops. So we get 71.85. 71.85. When we divide it, we get 7.863647, etc. moles of FeO. And we have 4 sig figs to work with. So this is going to be 7.864 moles of FeO. Let's have a conversation about what I expect to see on a test. Because you know that my tests very often say things like, no work, no credit. Do I need to see your crisscrossing for formula writing? No, I don't. But you need to write the formula someplace. And if you're not consistently getting formulas right, you probably need to write it down, not for my benefit, but for yours. There are still formulas that I don't do in my head. And I've been doing chemistry longer than you've been alive. I mean, I've only been teaching it 7 years, but I mean, my first brush with chemistry was before you were born. Just let that sink in. I'm old. And there are still formulas that I write, I will jot down. You know, I don't go through a real formal process at this point in my life, but, you know, for something that's got funky, weird charges, like, I write it out. And it's not for anybody else's benefit, it's so I don't screw it up. So, you know, I don't have to see that. Do I have to see this? I should someplace. I think that's really useful. That's both for your benefit and for my benefit, because if you do screw it up, having that on the paper allows you to retrace your steps. So this is the sort of metacognition. The thing that we can teach is orderly, sequential thinking about your own thinking. And that's really critical. Metacognition is thinking about your own thinking. What's your thought process? The more of your thought process you put on paper, the more you can trace back your footprints in the snow to see where you made mistakes. So that's really important. So I should see some variant of that. And of course, I have to see a factor label. Most of you are doing that. You have to label things. I have to see units and chemical. Why? This is Chapter 7. In Chapter 9, we will suddenly be doing factor labels that involve 3 units and 2 chemicals. There'll be 5-step. So you have to be in the habit of writing both the units and the chemical. I do it myself. I don't leave that out for myself. Even when I'm just, and you know, I do this. You know, if I'm like at home after my daughter's gone to bed and I'm thinking about something and I'm thinking about a particular chemical reaction and I'm writing something down, if I'm doing stoichiometry, I write the units and chemical even when it's just for me. Because otherwise you have no idea what those numbers are when you go back to it. You're piecing it together. So you do need to, you have to do that. Which gets us to number 3, which is a larger step problem. And it's one that you won't see too many of, but you should be in, you know, it was a refresher. So, how many molecules are present in 726.41 grams of carbon tetraiodide? So first of all, we need to write a formula. This is a prefix name, so this is obviously molecular, and it's Ci4, carbon tetraiodide. This sucker is heavy. Iodine is a massive atom. So carbon tetraiodide is super heavy. So of course we want to write our given first, 726.41 grams of Ci4. Well, to do our next step, which is going, this is GMA, okay? We're going from grams to atoms, but it's not atoms now, it's molecules because it's a compound. So we have to go through the valley of the moles. You have to go through moles to do this. So how many grams of Ci4 in 1 mole of Ci4? And then we know how many molecules of anything in a mole of anything. What number is going to go in that last spot? 6.022 times 10 to the 23rd. Molecules of Ci4. So this is the one piece that we have to get. We have to get our molar mass. Carbon is pretty light, 12.01. Iodine, woof, 126.90 grams per mole, and we got 4 of them. So we have a molar mass of 519.61 grams per mole. That is massive. So 519.61. Multiply across the top, divide across the bottom. Lovely, lovely. You haven't done one like this in a while, and the one thing that some people forgot So we can do 726.41 times 6.022 divided by 519.61. And then that whole mess is times 10 to the 23rd. So what we end up with, and it's actually nice because you don't have to move decimals, it ends up nicely, 8.418700602 times 10 to the 23rd molecules. We have a whopping 5 sig figs, 1, 2, 3, 4, 5, so we can go out to there. So our final answer is 8.4187 times 10 to the 23rd molecules of Ci4. Okay. This was the one on the front that was most missed. I think people freaked out when they saw molecules and they forgot about Avogadro and how many molecules in a mole. They wanted to do all kinds of weird stuff. That was pretty common. So lots of people missed that one. And a few people kind of, I think, had a brain fart and forgot how to use scientific notation and forgot to put it in there or had a negative. So just a brush up there. Just a reminder. Okay, let's go to the back. These are your percent comps. But, you know, in truth, 2 out of the 4 of them were naming and percent, or were formula writing and percent comp. You're, in essence, being assessed on your ability to do both of them. You have to be able to do one in order to correctly do the other. So for the first one, it was easy because you were given the formula. And we want to, now the one pitfall a few people fell into, determine the percentage composition of each element in the following. So that is literally each element, nitrogen, oxygen, hydrogen here. A few people wanted to do the percent comp of each ion, and so I had some people who tried to do, well, it's this percentage ammonium ions and this percentage nitrate ions. You can do a calculation like that. There are situations where that's a useful calculation, but more commonly we do percentage of elements. And when we start doing what we're going to do in the second half today, you'll see where that comes into play. Okay, NH4NO3. So we've got nitrogen, hydrogen, and oxygen. And this has a molar mass of 14.01. We have 2 of them, 1, 2. Hydrogen, 1.01, and we have 4 of them. And oxygen, 16.00, and we have 3 of them. So this is 28.02, 4.04, and 48.00. Total is 80.06 grams per mole. Now, do you absolutely have to write that? No, but it sure makes, you need to have something like this. This is the step that I sometimes skip, but especially it makes your work easier because you've already calculated it when you did the total. If you write it down, then you're just going, oh, okay, well, 28.02 divided by 80.06, because you've got those numbers recorded. You're not going back and re-adding them. Every time you re-add them, of course, there's the chance to make a mistake, to hit the wrong button or do something. So this gives you 0.3499. 8750, blah, 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 with sig figs, and this was the trickiest one of the sig fig rounding. Lots of people had sig fig rounding problems. So we have 4 sig figs here. That brings us to here. The next number is an 8. What does that do? Rounds up. Well, the number in front of that is a 9, so that rounds up. So with correct sig figs, this becomes 35.00% nitrogen. Okay, and that's just a sig fig thing. But those are the trickier ones in terms of rounding. Hydrogen. Every 1 mole of ammonium nitrate contains 4.04 grams of hydrogen to 80.06 grams of compound overall, so we get 0.050. etc., and that ends up being 5.05%. Note that we only have 3 sig figs here. It's a different number of sig figs because the sig figs are governed by the numbers that you put into that particular calculation, not by the overall problem. Okay, and then last but not least, we have oxygen. Oopsie. Stick that up there. And oxygen, in every 1 mole of this stuff, we have 48 grams of oxygen to 80.06 grams of the total compound. We end up with 0.59955, etc. And it ends up being 59.96% oxygen. Okay? Questions, comments, concerns on that one? The ones where you, yes, sir?
The only question I have is, we're doing it at 100% composition. How is it able to add up over 100%?
Because you're rounding.
Okay.
You're rounding. You shouldn't be looking at, remember, because I said don't ever like say, oh, okay, well, I got these two, 100 minus these. Yeah, don't do that. You're rounding. I mean, these decimals go on for a really long way. If we took those out to 8 decimal places, we'd probably be looking at something like, 100.000000012, blah, blah, blah. The atomic masses are rounded. That's a good question. Or you might get 99.999999. Yeah, these are not exact numbers. We can't get perfect numbers. So we're doing the best we can. And 2 decimal places is more than sufficient for the level we're working at. Okay. For the most part, people did fine when they were given the formula. So sodium sulfate. First thing you got to do here is write a formula. And I will tell you that on my key here, because when I do a key, I'm taking the quiz just like you are. I'm just taking the quiz. I wrote down, that was the first thing I did. Oh, okay, sodium sulfate. Yeah, okay, that's Na2SO4. Okay? Because if you screw up the formula, everything else falls down. And now we're looking for the percent composition of everything. So we have sodium 22.99, and we have 2 of them. Sulfur 32.07, just 1. And oxygen is 16 times 4. And I didn't actually write down my intermediate numbers. So this one's 64, 22.99, 44, 46 point, no, 45.98, 45.97, 98. Oh yeah, it would be. Okay. Okay, 45.98. So total mass of the substance, 1 mole of sodium sulfate is 142.05 grams per mole. Now we'll shrink this and stick it someplace. When we start doing the big stoichiometry, reaction stoichiometry in Chapter 9, every single time I start a problem, I do this for all the compounds that I'm working with on my paper. My papers are covered with that stuff. And I just make little notes to myself for the molar mass of every single compound I'm working with. Because you'll be working with 4 compounds, and you'll have to do stoichiometry problems that involve maybe 3 of them. So I always just jot those to start with, and then I've got it. It's the first thing I do. Okay, so percent of sodium, we have 45.98. Oh yeah, there it is. I wrote it down. Divided by 142.05 grams. We're saying that in 1 mole of this stuff, we have 45.98 grams of sodium to 142.05 grams of the compound, 0.323688.
Hear that from?
Probably not. Okay. And so what we get is 32.37% sodium. And for sulfur, we have 32.07 divided by 142.05, and that gives us 0.22576, blah, blah, blah. Multiply by 100, we get 22.85 when we consider sig figs, percent sulfur. And then for the oxygen, 64 divided by the 142.05, we get 0.45054, etc. And what we end up with is 45.05% oxygen. Okay? Questions on that? For a lot of people, their process was perfect, but their formula was wrong. And if your formula was wrong, everything else falls down. So, in terms of that whole 100% thing, here's where looking at do these things total to 100 is useful. I had a few people who made errors that were serious, where they had if you added up their percentages, it was 170%. Okay, you have a problem. Or your percentages total, I don't even remember if that was in this class or the other. Their percentages total to 73%. You have a problem. If you're totaling to 99 or 101, you're fine. If you're totaling right up against 100, it's a rounding thing. If you're way the heck off, it's a larger problem. And so it's a good thing to keep a rough gauge and go 30, okay, 33, 28, and 45. Yeah, that's close. Okay, so calcium chloride, I think everybody got this right. This was one of the easier ones because I gave you the formula and it was only two things. And has anybody looked at a bag of de-icer in the last few days? I just looked at the bag of de-icer in our garage, and guess what? It says calcium chloride de-icer. So it's CaCl2. You can go get CaCl2 pellets pretty much at any store right now. Okay, times 2, so we have 110.98. The calcium is 40.08 grams divided by the 110.98. We get 30. I think we did this one as an example, didn't we? And I'm going to speed this up because this was one that people did pretty well on. After we divide that and multiply by 100, we get 36.11% calcium. Let's move that up. And then chloride, we have 70.9 grams of chloride in every 110.98 grams of the compound. So once we divide out and multiply by 100, we get 63.89% chloride. Okay? As I said, that was the one people did the best on. It was simple. 2 parts, 2 pieces, and you got the formula. And then number 7. Ooh, that was a stinker. Nobody loves the stock system at all. This is my contention. No one loves stock naming. Okay. So we have lead 4 carbonate. A few words about memorizing symbols and names. I don't do the whole thing of memorize the first 20 on the. I think that's stupid. But I give you one that doesn't have names, so I kind of force you into it, and you just basically get proficient by using this. Pretty soon, suddenly you know all these things that you didn't know you knew. On the metals, the names are back here with the symbols. So if you forget what lead is, if you look at the back for your transition elements, they're all right there, which would have helped a few of you. Okay, I will finish, stop. Oh wait, we have another period. We come back, okay. We'll finish this when we come back. We had finished talking about calcium chloride, and we were going to talk about lead 4 carbonate, and I mentioned to you that as a nice little cheater, you can use the fact that the names and the symbols are all written on here. You've got a really good resource. So that's fine. Hey, this is why we take FIPs. We don't do this on the test. So we have lead 4 carbonate, which is lead 4 plus. The carbonate, oh well. The carbonate ion is CO3 2 minus. So, again, with the importance of good formula writing, we know that this looks something like if you're doing your crisscross, there's an intermediate moment where your formula looks like that. But you have to simplify. You can't leave it like that, because I had people who figured their molar mass based on that. And that gives you twice the molar mass that you should have. So your formula is just Pb CO3 2 times. We have to reduce those. That's not optional. Okay, so let's shrink that. And let's look at what our, and I'll just get rid of that altogether. Let's look at what our percent composition is going to be. So we've got three elements that we're working with. We've got Pb, C, and O, so lead, carbon, and oxygen. Lead has a mass. Lead is heavy. I will say this. It's completely intuitive. It's completely obvious. And yet, it's astounding. A piece of lead pipe is heavy because lead atoms are heavy. It's literally that. It's down to that level, which is completely intuitive to me. Maybe I'm alone in this. Both completely intuitive and completely mind-blowing. Like, heavy stuff is heavy. It's got a lot of mass because the atoms are heavy. Hydrogen atoms are really, really light. If I give you a box of solid hydrogen, it's gonna weigh, if I give you 100 milliliters of hydrogen and 100 milliliters of lead, the lead has got more mass per unit volume. It's more dense because its atoms are really heavy. I find that kind of neat. Down to the atomic level. Okay, maybe nobody else does. So anyway, lead, it's heavy. We have 2 carbons, and we have a whopping 6 oxygens here. So a few people somehow missed that and thought that there were 3 oxygens, but you've got 2 actual carbonate ions for every single atom of lead. So this gives us, 96, 24.02, and that's all by itself. Our total molar mass for this stuff is 327.22 grams per mole. So once you've figured that part out, you're just about home free because you're all pretty good at doing percentages. You've been doing them on your tests since day one. The minute you get a test back, you immediately start doing that. So for lead, we have 207.2 divided by 327.22. After we divide it, we multiply it by 100. Here, we'll just do that. We get, and sig fig it, 63.32% lead. For carbon, we have 24.02 grams of carbon in every 327.22 grams of the compound. Once we sig fig it, we get 7.341% carbon. And then oxygen is our last one. Shrink those. And oxygen, we've got 96 grams of oxygen for every 327.22 grams of the compound. Multiply by 100, we get 29.34% oxygen. Okay? So again, most of the mistakes I saw were not in the final step, they were in the preliminary step. So if you tripped over your feet on formula writing, you need additional practice. Look in the book. I can see what I can find online. You're welcome to do my practice sheet as many times as you want, but it's not like it's new problems. So that's it. Questions, comments, or concerns on any of the stuff on that FIP quiz? 9? Okay, so we'll stop this recording. We'll break off. I'll give you a minute to get out your notes, and we're going to finish up one last concept.